Hello and welcome to this tutorial which is dedicated to the modeling and analysis of a plate girder bridge with parabolic haunches. The important thing here to note is that we have checked this box, the haunched girder checkbox. The rest is fairly standard. This is the length of the girders. We have 3 girders. This is the spacing between the girders. These are the material properties for the steel. All of this is fairly standard. We have 4 supports. We have just one pin support at pier number 1. The same applies to the other girders. We have 17 points along the girders where the cross-sectional properties do change. Here is their location. Same applies to the other girders. We have 27 stiffeners along the girders. The spacing is equal to about 26 feet, and so you can use these buttons to help speed up entering these values here. Side 3 here means that there is a stiffener on both sides of the web. Now that we have the stiffeners defined, we can enter the cross frames. We have 27 cross frames which are attached directly on the stiffeners. 0 here means that we have full cross frames. We don't have any type of lean-on cross frames. The same applies to bay number 2. We have one additional reference point per girder, which corresponds to the top of the haunch in the central portion of the bridge. If we do not define this point, the program will have issues modeling properly the haunches, okay? And this point does not correspond to any stiffener or brace location. This is why we need to add a reference point here to properly define it. We don't need to click on this button because the model is already run, but if this is the first time you come across this form, or if you change any location, or if you add or remove any reference point, you would need to click on it again. We have a mesh size of about 3 feet, except on the segments where we need a slightly finer mesh. You can just enter 36 here and hit apply, and then the program will automatically find for you the optimal mesh size. We have 9 cross-sectional profiles, and one thing you will notice here is that there is no column to define the web depth, okay? And this is specific to haunched girders. There is a further form in the preprocessor that allows you to do this, but here we're just concerned about the top and bottom flange thicknesses and widths, and also about the web thickness. We can still assign a profile, a specific profile to each of the segments as shown here, but the real fun for haunch girders will come now, where we are really defining how's the haunch, what is the depth at each of these sections. So the convention here will be to say that this will be haunch number 1, and then haunch number 2, haunch number 3, haunch number 4. This is just a convention, okay? This is for the program to automatically find the equation of these curves. What we need to define is only the web depth and elevation at the start and end of each of the portions of these haunches here. So this is what we're doing here. We have haunch number 1. Well, actually, let's be fully transparent here. We have, let's enter 0 here for you to show how it works. Initially, the bridge is flat. So you can see here the web depth starts at 0, at 72, and it's still 72 at 105 feet. We have -1 and -1 because the bottom flange thickness here is 1 inch thicker than at the start. By convention, this would be haunch number 1 and haunch number 2, even though this portion of the bridge is flat. And then at 105 feet, this is where the haunch really starts. So we have haunch really, the convention will be to name this haunch number 3. And what we enter here is just the web depth at the end of that haunch, which is 144 inches. So double that web depth here. This corresponds to pier number 1, of course. And this would be the elevation at pier number 1. Then the haunch comes up again. So we have haunch number 4. It goes up to the central portion. So again, you can see here that additional reference point at 340 feet. This would be the elevation at that point. And the web depth is back at 72 inches. Now the haunch goes down again. So it's haunch number 5. elevation minus 72 inches, and again 144 inches for the web. And then back up again, 72 inches, and finally the flat portion on the end, so haunch number 7 and 8. This is just a convention, of course. This portion of the bridge is flat with a constant web depth of 72 inches. These are the few points, the few parameters that you need to enter. You can see here we've got 40 segments, and all you have to do next is to click on this button, which will automatically calculate the equation, the elevation at the start and length of each other segment together with the web depth. So we believe this is a really useful way. We've tried to make this as easy as possible. You just need to define the web depth at the start and end of the haunch portions here, together with the elevations. You don't need to enter this for all of these segments. This would be extremely tedious. You just need to apply these numbers, to define these numbers at the start and end of the haunches. We can now go to the next form, which is the erection sequence form. We have a drop-in member here between end 1 and start 2. You can see that these points are disconnected, and you will need to wait until stage 2 to have the girders fully erected. We have here this form where we are turning on the cross frame whenever the girders on either side, on both sides of the cross frames, are themselves active. So you see here between cross frame 11 and cross frame 17, you will have to wait until stage 2 to have these become active. This is because of the drop-in member, of course. We are running an eigenvalue buckling analysis for stage 2. This is the search interval for stage 2 together with a subspace dimension, which has to be at least equal to the number of modes within that interval. This is just a shortcut, okay, to make the solving of the eigenvalue problem faster. You don't need to go into this level of details. You need to go into this advanced button here. We can click on run, but instead we've got the model already run. So let's go to viewer instead and look at the drop-in member. Let's zoom out, and you can see the uniform cross frame spacing together with a flat portion initially, followed by the haunch, a deeper web depth here, and same on the other side, symmetrically. You can check your plate thicknesses by clicking on this button here. This is a really nice way to check visually your cross-sectional assignments. If we look at the linear elastic solution, we'll see that we have actually something not totally surprising. We have a rigid body translation here. Okay, this is a common mistake that is done sometime when we have a complex erection sequence. This is not very complex here, but remember the pin is located only here. So this portion of the bridge is free to move in the longitudinal direction, at least at this stage. So what you would need to do to fix this is either enter pin supports here instead of rollers, or define and assign dummy springs in the longitudinal direction, whether here or there, actually anywhere along the bridge here, of this portion of the bridge. Now let's go to stage number 2, where we see that the bridge is now fully stable and the maximum displacement is equal to about 2 inches. One thing you can do is checking the support reactions. We have a reaction of about 27 kips at the ends and of about 130 kips at the piers. You can also look at the stresses. These would be the longitudinal stresses, and at the top face here, we would have a maximum tension of 4 ksi at the piers and a minimum compression of 5.5 ksi at the mid spans here in spans number 1 and 3. Something else you can look at is at the moment and shear diagrams. So if we go to stage number 2 here by convention, okay, the moment is taken equal to 0 for the drop-in member. Okay, this is just a convention. We can go to stage 2 instead. This will be the final bending moment diagram. If you go to the shear diagram, you will see that the jump in the shear here at the piers is equal to about 64, 65 minus 66, so this is about 130 kips. This is what we found visually looking at the support reactions. And same on the far ends here, it would be equal to about 27 kips, which is what we found visually. Finally, let's look at the buckle shape. We see we have a global lateral buckling mode. Let's increase the scale of this mode and let's make the bridge dense a little bit. This mode is pretty high at 8.7, so this is a fairly stable system. No stability issue here. Of course, you would also need to look at the placement analysis to check the stability in further stages. But I hope anyways this tutorial was useful in providing you an explanation on how to model this type of haunched girders. Thank you very much.